Quick problem today. This one is going to be an inclined plane problem. And so this is our initial configuration. This is a basic inclined plane problem. What we want to know is what happens when the mass is lowered. Um, what happens when the mass is lowered such that the spring at the base is compressed? And then we're going to write an expression in terms of the mass compressing the spring for the spring's length. And so we are going to see what happens when essentially the spring and the mass system are in mechanical equilibrium. So the mass is going to be allowed to roll down the inclined plane and make contact with the spring such that the spring is compressed. That is the system that we're analyzing. And one thing that it's useful to do is take a look at the coordinate system. What would be a useful reorientation of the coordinate system, staying away from our normal x and y? Well, let's define a new coordinate system. What happens next is we can label the forces on our mass. So because we've rotated our coordinate system, this one is going to be mg. Let me draw the triangle. This is the side adjacent to the angle theta. This one, I can use the principle of transmissibility to translate this vector up here, and this is the mg sine theta. Because our forces need to balance, in order to hold this in place, we've got to be applying some tension force on this rope to balance it out in the x prime direction, and then the normal force associated with the weight of the cart. And we have everything we need to start writing our kinetic equations. Okay, so these are not kinematic equations. We're not dealing with forces. And kind of just analyzing the new coordinate system, x prime, y prime, I can see that the net forces in the x direction, in the x prime direction, equals 0. And also the net forces in the y prime direction equals 0 as well. It's worth reiterating right now that these are the conditions for which the system is at mechanical equilibrium. This 0 indicates that mass times acceleration is equal to 0. And well, the mass is not 0, right? The mass of an object can never be 0. So that means that the acceleration is 0, which means the velocity is not changing. That means that the object is stationary and all of the forces cancel out in those directions so that we have a stable configuration in mechanical equilibrium. Okay, so let's just draw a diagram of the spring. I'm going to rotate the axis so that, like this. So I'll draw the cart in contact with the spring, so as if the spring is compressed. And then I'll draw the spring like in its first state before it was compressed, so we can kind of see it's not as compressed in the blue. Now the amount that it was compressed, we're going to call delta x prime. And we know from Hooke's law that the force compressing or stretching a spring is some proportionality constant k multiplied by the change in the length observed in the spring. All right, so all we have to do is write an expression for the change in the spring's length in terms of the mass compressing it. Okay, so that means that we need to write our kinetic equations. In other words, we need to write the sum of the forces. So it looks like if I just look at this right here, we have this mg sine theta acting in the negative x prime direction, and there's no longer going to be this tension. Once he releases this and it goes down, the mass of the cart is just going to be resting here. So there will no longer be this tension force from the rope. So what there will be, however, and I'll just draw it over here on our new diagram, is the force mg sine theta compressing the spring, and then the force from the spring pushing against the mass. And since we've defined to the right to be positive for x prime, we can write the sum of the forces just like this. When they are in mechanical equilibrium, this will equal to 0. And then doing some quick algebra, we can write our expression for the change in the length of the spring in terms of the mass. One thing is worth mentioning is that it may be useful to, at this point, employ numerical software with this formula that you've written so that you can test multiple spring and mass configurations. And I think that this is a good exercise for programs like MATLAB or Excel. That's going to wrap it up for this video. I hope you guys all enjoyed. Thank you for viewing. If you have any questions, please leave them in the comments. And if there's anything you'd like me to cover in the future, please leave that in the comments as well. Thank you for viewing. Have a wonderful day.